think, Harry, you should see it when it comes on and you take over.
Okay. Right, ladies and gentlemen, welcome back. Just to emphasise what we talked about in the previous 50 minutes or so, that actinides can have a variable oxidation state, but some of those oxidation states are more stable than others. In the case of both uranium and plutonium, we're talking about the 4+ and 6+ oxidation states being the more stable compared to the others that can exist under certain conditions. And the oxidation states can be influenced by the environment in which the uranium and/or plutonium finds itself in, for example, which will become clearer after lunch when we talk about, hang on a minute, where's my presentation gone now? Oh, I can continue, don't worry. Which we'll talk about later in the afternoon, to do with the recovery of uranium from ore bodies, its conversion to various intermediate products before we actually make nuclear fuel. Why? Oh, okay. So this is going to be the second part, and we will emphasize in a little more detail the various process technologies we discussed earlier, whether it be ion exchange, liquid-liquid extraction, precipitation, etc. And in this second part, there'll be a little more chemical engineering thought or implications in the presentation. So hopefully we'll have gathered some knowledge about the chemistry of the actinides, and sufficiently, so hopefully, for you to be able to discuss why certain processes are employed as opposed to others. As it indicates there, we're going to build on the first part, but we're going to be now providing more chemical engineering aspects. So ion exchange. This is what's happening in ion exchange. You remember I used the example of deionized water. This is in actual fact is what is happening in deionized water. You have what's called a cation exchanger, and the cation exchanger obviously is all about exchanging ions. In this particular case, sodium is the example, for a ion that's attached to the actual resin, i.e. the solid H, okay? And it's the proton that we are exchanging in this particular case with, or for sodium. So sodium is in the aqueous phase, it's in the water that we're wanting to deionize, and the ion exchange column is in the hydrogen form. And what happens is that the sodium exchanges with the hydrogen ion to give us hydrogen in aqueous solution, and now the sodium is residing on the ion exchanger, on the solid. And a very similar aspect with the cations, beg your pardon, with the anions, where in this particular case we have nitrate ions reacting with the solid phase, with the ion exchanger, and exchanging chloride ions, and chloride ions finish up in solution. But if this was, for example, water, what we would have with the anion exchanger, we wouldn't have chloride ions on the anion exchanger, we would have hydroxyl ions, such that when nitrate, as it's indicating there, exchanges with the OH ion, then in solution we'll finish up with OH minus. And then you don't need to be much of a chemist to realise that we've produced H plus and OH minus in solution. So when we add these two equations together, we finish up with H2O. And this is what's happening when we deionize water. We're exchanging all of the metal ions, the calciums, the sodiums, the magnesiums, for hydrogen ions, and we're exchanging all of the anions, the nitrates, the chlorides, the sulfates, the fluorides, for hydroxyl ions, OH minus. Such that when they combine, then we have simply water. Okay? And it says there, this exchanger, whether it be an anion or cation, can be fairly selective depending upon the ion, i.e. in this case, the sodium or the nitrate valence, the size of the ionic form, ionic strength of solution, type of functional group, nature of non-exchanging groups. Okay, all of these can be important in ion exchange. But the essence is basically to exchange and selectively remove ion in solution that you actually want to conduct a future series of reactions with. And not surprisingly, the chemical engineer will look at from an ion exchange point of view, the physical and chemical properties, the physical properties of the ion exchanger itself, its density, resistance to osmotic shock, beg your pardon, diffusion and relative porosity. And then when if he's weighing up the chemical properties, hydration, ionization, selectivity, all of these, when you're developing a ion exchange process, you will have to give consideration to. And as I said earlier, ion exchange is important in uranium mining, irrespective of the leaching process, which we'll discuss after lunch, irrespective of the leaching process we use. The actual operations at Springfields, when we used to operate a uranium refinery there, and still, but with Magnox only at Sellafield, the actual process we use for recovering and purifying uranium and plutonium at Sellafield, and as we use to purify uranium at Springfields, is this process called liquid-liquid extraction. When do we use liquid-liquid extraction as opposed to ion exchange is something that you need to appreciate, and normally liquid-liquid extraction will be used on more concentrated solutions, i.e. let's assume any uranium in solution above 10 grams per litre, you would probably more likely consider liquid-liquid extraction. Anything down at 1 gram to 5 grams and less than 1 gram, probably ion exchange would be the preferred separation process. In liquid-liquid extraction, as I'm indicating there, we use what's called this countercurrent flow. So in other words, the actual extractant, let's use TBP as an example, TBP in odorless kerosene, which is immiscible with the aqueous phase, and let's assume that's uranyl nitrate. What happens with countercurrent flow is the more concentrated uranium solutions meets up with the slightly less concentrated TBPOK. And the reason for that is, if you look at this particular overhead of the illustration below, by the time you're down to very lean uranium concentrated in your aqueous phase, that aqueous phase is meeting up with fairly lean TBPOK. So in other words, the TBPOK has got the maximum power to extract that very dilute uranium out of its aqueous environment. Full stop. And none of these, certainly liquid-liquid extraction and ion exchange, none of these processes are carried out on a single contact. There are multiple contact systems to ensure we've got the most effective extraction of, in this case, uranium out of solution. So where you've got a very low metal in solution, then you would want to use the, in inverted commas, the virgin liquid-liquid extractant, i.e. TBPOK, to make sure we can pull out that remaining very small quantity of uranium left in solution. So what are the requirements as far as our industry is concerned, our nuclear industry? Excuse me. They need to be able to, certainly solvent extraction, because of the quantities we are talking about, probably at something in the region of 300 grams per litre. They need to handle a high throughput and a fairly high concentrated solution. Springfields had the capacity to be able to process something like 10,000 tonnes a year of uranium ore concentrate. And that, to be quite honest, is a significant amount of material to be handling using a chemical process. They have to be able to operate under a wide variety of flow rates and temperatures. However, you need to make sure that the process parameters you're using can accommodate those changes, as we'll talk about when we talk about uranium ore processing and reprocessing of spent nuclear fuels. Not surprisingly, for reprocessing, they're going to have to operate in a highly radioactive environment. Again, we'll pick that up later. Be remotely operable and maintainable. Certainly operable is key to the operations at Sellafield. Maintainable, it will be very nice, but it's not always possible to achieve that for obvious reasons. Operate efficiently. There's no processing, there's no reason not to operate efficiently. In fact, you wouldn't operate if you couldn't be efficient. Handle solids, preferably, but in many instances the process technology does actually remove solids away from the aqueous phase before it is contacted with the organic phase, i.e. the TBP odorless kerosene phase. And in the nuclear industry, and not solely the nuclear industry, but the pharmaceutical industry, you can select a mixture of contactors. I emphasize the word contactors, ladies and gentlemen. If there is an examination question that talks about liquid-liquid extraction, please remember it is contactors and not contractors. I've had many examination answer that talks about BNFL being a contactor, because obviously they've misunderstood the difference between a contactor and a contractor. Okay, so we have three different types of contactors: mixer settlers, columns, whether packed or pulls, and centrifugal contactors. And for the next few slides, we'll talk about the difference in these particular pieces of equipment. This is illustrating what a mixer settler is about. As you can see there on the far left of that illustration, that is the excuse me, that is the mixer. This is where the two phases, the aqueous phase, i.e. the uranol nitrate solution, and the solvent or the organic phase, the TBPOK, this is where they're mixed together at a speed round about 300 revolutions per minute. Nothing like your Black & Decker power drill that's operating at a few thousand revs per minute. And the reason for that is because we want to engage the two phases together, and what tends to happen is one of the phases as a result of the stirring, you produce droplets in the other phase, and normally for extraction you would be producing droplets of TBPOK suspended, for want of a better word, in the aqueous phase. And the reason you've done that is because obviously those fine or relatively fine droplets have got a very large surface area that will allow the exchange of uranol nitrate in the aqueous phase to pass into the organic or solvent phase, TBPOK. So this is why in the forward extraction you always have your solvent phase in suspension in your aqueous phase. But you don't want too fine the droplets, hence why we're not whizzing these two phases around at 3,500 revolutions per minute, but more likely something in the region of 300 revs per minute, because they then pass into this part here. This is a mixed phase port here. They pass in through the mixed phase port into this part of the contactor, and that is the settler. This is the mixer, this is the settler, okay? And as it says, what's happening in that settler is the two phases disengage. The droplets coalesce, they produce a layer, and that layer for TBPOK, now loaded with uranol nitrate, is the lighter phase, and it's up here, okay? And the aqueous phase, being more dense, is at the bottom of the settler. And that's what happens in a mixer settler. It does say here about, in some instances, the mixer, the actual impeller here, can be designed so it can actually pump, which we'll talk about in probably in UOC conversion. That is not the case in the nuclear industry. The actually movement of the liquids, etc., once it's in the settler, the actual aqueous phase can go one way, and the organic phase, solvent phase, now loaded with uranium, can go a separate way, because there are weirs for the organic phase and ports for the aqueous phase, okay? And they can go in separate directions to be contacted again with more TBPOK, because as I indicated earlier, it is not a one contact stage. Now, in our industry, because we are not pumping these, we've designed a mixer settler so these liquids, when they're separated, can flow in different directions. And we call this an integral box mixer settler. And you'll see why it's integral when we discuss uranium or concentrate processing. So what are the mixers? Why would you use a mixer settler compared to the other two forms of contactors? And it says here, and I'll not go through them, they're fairly self-explanatory. They're fairly low capital cost, which is important, but in our industry, not crucial to that extent. Limited instrumentation. Once we've set them up, once we've adjusted the weirs, full stop, then we can get the liquids to flow in the right direction. The flowing of the liquids, as you can probably now well imagine, is dependent upon the densities of the two phases. Excuse me, and as we will talk in the afternoon session, attribute, it's got a large solvent inventory. In other words, these settlers, the settlers are roughly about 5 to 10 times the size of the mixer. And what you're looking for in a settler is not the volume. You're looking for the surface area. You're looking to allow the two phases disengaging so that we have an upper layer and a lower layer. So surface area is more important than volume when we're looking at settlers. Long residence times for processes with slow kinetics, geometrically safe design as limited capacity. Both of those two, as you will see when we're talking about reprocessing, will be challenged, full stop. What are the control requirements? Certainly the mixer speed. As I indicated earlier, you don't want the mixer thrashing around at 3,500 revolutions per minute. Otherwise, you will produce an emulsion very similar to, well, not similar, but salad cream that you put on your salad, for example. That is an emulsion, a very stable emulsion for obvious reasons. Interface in settling chamber is controlled by overflow weirs, etc., etc. Okay. What about the next choice of contactors? Both mixer settlers and columns have been used, and in magnets, certainly not columns, but certainly with Thorpe, columns were used in Thorpe. And unlike mixer settlers, it's a differential type of a contactor. So in that particular column, as I'm illustrating on that PowerPoint, that you've got a number of what's called theoretical plates. In other words, a number of individual mixer settlers, where you've got mixing and then settling, etc. And how is that achieved in a column? Excuse me. It's very, well, yeah, very simple to a chemical engineer, may not be to a chemist. Is these plates that are inside the actual column itself, and the plates are perforated. And this particular column we're illustrating is a pulse column. So in other words, you're pulsing the liquid in the column such that when the liquid passes through these plates, then it forms droplets again. And then when it gets to the next plate, it probably has coalesced. And again, the similarity between a mixer settler and the pulse column is that these phases, the aqueous phase and the solvent organic phase, the TBPOK, are passing countercurrently. So invariably, the aqueous phase will be falling down the column or passing down the column, and the solvent phase is coming up the column and passing through these plates, etc., and creating this efficient contacting. The challenges with the pulse columns or any columns is that to achieve the efficiency that you're looking for, and bear in mind with a mixer settler in the extraction stage, we're looking for about 7 to 8 stages. Then obviously you need to have something like 7 or 8 theoretical stages in your column. It makes the columns fairly tall, and as it says there, we could be talking about a column that's 5 to 7 meters in height. That will impact, and that's something else that the engineers have to consider, that will impact on the size of the actual reprocessing building itself, because this will be by far the tallest piece of equipment you would have in a reprocessing operation. And there it's talking about pack columns and pulse columns. What I've just been talking about is more, let's say, more pertinent to pulse columns, but you can have pack columns. Pack columns, as it indicates, rather than have these plates attached to a central axis of that supports them, these pack columns are literally have got packings that are, I was going to say, thrown into the column, let's say placed into the column, and you've selected your packings for various reasons, whether it be construction purposes. At Sellafield and at Springfield, we would always be talking about stainless steel because we're using nitric acid. And the packings would be for a pulse column, if we use them for reprocessing, again would be stainless steel, possibly with a neutron poison incorporated into those packings. And all that the packings are doing is making the movement of liquid both downwards and upwards in that column, making a fairly tortuous path, such that two phases actually come into fairly good contact with each other. And that's what either a pulse or pack column is about, is to make sure that you've got good distribution and good contact between the two phases. What would the chemical engineer or even the engineer be thinking of when we come to their operation? Operation is not necessarily something that a chemist would necessarily be too engaged with. It may be, he or she, but they would leave it to the chemical engineers because they understand probably understand better the hydrodynamics systems that need to be engineered into the separation process. As it says there, the solvent phase, the light phase, is circulating from bottom to top. The aqueous phase is going in a different direction, depending on what you're trying to extract out of the aqueous phase. That would determine which would be what's called the continuous phase, i.e. in this case, the aqueous phase would not be in droplet form. That would be the organic phase, as we discussed with mixer settlers, for example. With a pulse column, as the word implies, you're getting this pulsing situation. And the reason why we chose pulse columns at Sellafield is when you look at the arrangement, and hopefully in the reprocessing section we will do so, there are no moving parts. That becomes important when we're talking about reprocessing, because the last thing we want, in fact, is for one of these pieces of equipment to fail. And bear in mind, when it fails, it is still in a highly active environment, radioactive environment. So actually retrieving it and mending it becomes, or repairing, beg your pardon, becomes a very, very big challenge. So where you've got no moving parts, and one of the reasons that Thorpe was a fairly high building is because it didn't pump any of its radioactive liquids. If the pump failed, then how do you move liquid from A to B, particularly if B is downstream? And what actually happened at Thorpe, of course, was most of the movement of liquids was by gravitational force. Okay, so what happens in a pulse column? in the actual, if you recall in the illustration of the column, there is what's called the pulse limb. This sits on the, if you like, outside the column, but parallel to the column, and it's the pulse limb that you're actually creating the pulse. You actually exerting a pressure and then relieving the pressure, exert a pressure and relieve the pressure, and this is what creates the pulse. Hence why we can get this good mixing of solvent and aqueous phases. Okay, and that's important. Where when you're designing something for reprocessing, you will always need to ask yourself, if it goes wrong, how do I get at it? How can I repair it? Because obviously in these highly active cells, you cannot send operators. And this is why in decommissioning, in N04, we talk about decommissioning processes taking a long time. Why? Largely, we're allowing the radioactivity to decay away and makes operations then more manual operable rather than relying on robotics. No doubt in the future, we will have come up with robotic systems whereby we can repair most radioactive pieces of equipment in situ. At the moment, it is still a fairly big challenge. So what are the attributes, of pulse columns, and what are the process control requirements? As the attributes, several meters of column needed for one theoretical stage. When we designed and built Thorpe, if we had not used pulse columns, then Thorpe could have been 2 stories lower than it actually was or is, because it's not been decommissioned as yet. 2 stories, something like probably best part of 5 meters. And 5 meters of 2 extra heights, storage heights, can add significantly to your capital costs. Okay, so had we not used them, then that Thorpe plant could have been a much lower height building, full stop. But you'll see why we selected them later in the reprocessing presentation. Low capital cost, yeah, probably equivalent capital cost to a mixer settler, as it says there. That's the important one, number 3 bullet point there. No moving parts. That's important for the time being, and probably even in the future. Although in the next contactor you will see that's slightly different. Well, significantly different. Requires large amount of head space, 12 to 15 meters, but little floor space. The pulse columns at Sellafield, for example, were no more than no more than 25 centimeters in diameter. And again, we'll talk about that in reprocessing, because safe by shape is something that we use as a controlling factor when handling materials that are capable of creating challenges for the industry. Moderate solvent inventory, less so than in a mixer settler, definitely. Because bear in mind, in a mixer settler, there's a lot of solvent held up in the settler stage, and again, it was one of the reasons why we chose pulse columns for reprocessing for Thorpe. Pulse column control requirements, pull frequency, pull amplitude, interface control. But the first two, frequency and amplitude, they bear in mind are controlled outside the radioactive area. Depends how frequently we provide the air pressure to the pulse loop. So that's fairly a simple control parameter. Interface control, both at the top and at the bottom of the column. Again, not a big concern, but it is needs to be considered when designing the columns. Bubble probes, I'm not sure if they were provided at Sellafield, I could be wrong. This is in more or less telling you, or trying to tell you, the size of the bubble, the number of bubbles and when they are disengaging, etc. Fixed spaces between probes. Most of these requirements are, if you like, a bit like a wish list. They'd be nice to have, but do they help us in a great deal of manner? Probably not, because the actual size of droplet will be determined by the holes in the pulse plate, okay? Interface location controls, etc. Again, if the chemical engineer has done his job, then this should be more or less fairly simple. Right, remember what I said about no moving parts. The nuclear industry, the reprocessing industry, is now thoroughly engaged with centrifugal contactors. And centrifugal contactors do have, obviously, moving parts. Now, the challenge can be overcome, of course. This is the centrifugal contactor. And as it says, basically, it's spinning the two, we'll come back onto the actual, we spin them. It's spinning the two phases together at a very high speed in comparison to a pulse column and in comparison to a mixer settler, the mixer part, at very high speeds, and therefore we will get much finer droplets. But also because the phases are being disengaged under the centrifugal force, then excuse me, the formation of small droplets becomes only secondary. It's not a major problem. It would be if the two phases had to disengage under gravity, but they're not doing, they're engaging under a centrifugal force. So these are now being favoured, and we'll explain why in the reprocessing presentation, or I think that could be on Wednesday. Okay, so why are these now being preferred? Well, they're much smaller, they're much more efficient. They can be clogged by solids, but you can remove solids by having an upstage centrifuge, and centrifuges are largely designed for removing solids from liquids. Okay, so why aren't there any moving parts in these? Well, what is not being shown there, but you can see the shaft. What is not being shown there, here's the shaft, and up here would be your motor. And the idea, of course, excuse me, is to have the motor outside the highly active cell. And this is what happens with mixer settlers at Sellafield. The actual motor that drives the pedal at 350 revolutions a minute or thereabouts is outside the cell. So if the motor fails, then no one's entering into a highly active environment. And similar with these. Excuse me, the idea is to have the motor situated outside the active cell. But with these, of course, you need to make sure that this the actual arm here, you don't get a great deal of whip because these are going to be operating at far faster speed than 350 revolutions per minute. So therefore, that axis you don't want to be vibrating too much, otherwise it will interfere with what's happening down in the actual centrifugal contactor itself. And as you can see, they have been used and are being used. And if we go to the Son of Thorpe, the second or third or fourth reprocessing plant at Sellafield, then you will no doubt they will see centrifugal contactors replacing possibly everything with the exception of the uranium purification cycle. We'll talk about that later. What are the attributes? Again, very similar to mixer settlers. They are discrete stages. Their efficiency can approach 100%. The efficiency when measuring mixer settlers, again, is pretty high. Offer a wide range of capacities and simple operation. Quick to reach steady state in terms of the solvent and aqueous phase. Requires, and this is a key factor, ladies and gentlemen, requires small amount of floor space and very, in comparison, very low headroom. Very small floor space that over, let's say, outperforms mixer settlers because their floor space can be significantly higher. Low headroom, as we've talked about, pulse columns and packed columns, you require a fairly high headroom. Small solvent inventory, another key aspect of selecting your contactors. Okay, short residence time, resulting in reduced solvent degradation, which we will talk about in the reprocessing lecture later in the week, or possibly, I don't think it's this afternoon, it's on Wednesday. Remotely operable, maintainable. That is largely true, provided the stirrer and the actual shaft of the mixer do not become disengaged or break. In mixer settlers, we have seen where the actual rotor, the bottom of the shaft, the actual impeller, I've seen that fall off because they've not been welded. These days, they'll probably weld the two together. But they can, obviously, those shaft and the impeller, they can erode in with time. Solids handling is an issue. And the reason for that, very quickly, ladies and gentlemen, the actual orifices and ports in these centrifugal contactors, as you can well imagine, because they are fairly small in comparison pieces of equipment, the actual orifices and ports are equally small and liable, if you've got solid, liable to foul. Requires motor in cell. That is not necessarily the case on every issue. It will depend how the cells have been designed, and also the actual how the centrifugal contactor is equally being designed. But speed, without a doubt, may require may require the motor to be in the cell, and therefore you would need to have some means of being able to disengage the motor away from the shaft because more than likely the motor has failed. Those are the requirements again, and we'll not go through those because we're probably getting a little near to lunchtime. Again, you can have variable speed. I'm not quite sure why you would. you would probably have selected the speed of the motor and therefore the speed of the actual impeller and shaft, but you can vary them. Equally, you could vary the speed of a mixer settler motor. Normally, one set they will operate or at that setting, full stop. Heat exchanger jackets can be included because in the liquid extraction process, you actually operate the extraction process at room temperature or as near as damn it to room temperature, but the back extraction where you are recovering the uranium out of the solvent phase, the TBPOK, that is operated around about 70 degrees centigrade. So again, with mixer settlers, having to heat up a fairly large volume of organic and aqueous phase is a challenge and a disadvantage when you're talking about selecting mixer settlers as opposed to pulse columns or centrifugal contactors. Equally, pulse columns will have to be operated at different temperatures, but with a column, as you can well imagine, it's easier to jacket the vessel than it is to try and jacket a mixer settler. So in terms of these pieces of equipment, which we've paid a good deal of attention to, but going back to the original ethos, chemical engineers play a crucial role in designing of plant and equipment and understanding its operation. They will certainly work alongside chemists because the chemists will have provided the data that the engineers will use in the various models that they use to calculate or design equipment, etc. But mixer settlers, as it says there, pulse columns have all been used. Centrifugal contactors are now appear to be gathering more and more, let's say, enthusiastic followers because they offer a good number of attributes. We have never used them in the United Kingdom, but that doesn't mean to say we would not use them if and when we re-engage, if you pardon the pun, with nuclear reprocessing. Each of the pieces of equipment have advantages and disadvantages. It's a bit like buying a motor car, whether you choose to buy a Mercedes or a high-performance Ford. Each have got their own attributes and disadvantages. To determine the appropriate piece of equipment, as we've indicated in that PowerPoint, you need to consider, or the chemical engineer needs to consider, a good number of conditions, etc., when selecting the piece of equipment. Obviously, had we had more, let's say, knowledge of centrifugal contactors, and we hadn't at the time, I can recall two of our chemical engineers going over to America, one to look at pulse columns, because pulse columns were a major change for BNFL in reprocessing. They also looked at mixer settlers. They were more comfortable in selecting pulse columns, and it would appear to have been the right selection. But to a civil engineer, it probably wouldn't have been, because he had to have an extra probably 5 to 10 meters on the height of Thorpe, which added to the capital cost. But we were not sufficiently confident that mixer settlers would be useful for Thorpe. A slightly different story today. We probably would look at not mixer settlers, beg your pardon, centrifugal contactors. We probably would look at centrifugal contactors with a much more clearer pair of spectacles. I think, Javad, that could be that last PowerPoint for my presentation this morning. If there are any questions, ladies and gentlemen, I suggest have a think about them over lunch and then raise them when we come back. It's 1 o'clock, Javad, isn't it?
That's right, yeah.
Yeah. When we come back at 1